Hey everyone, welcome to yet another session of the Generative AI Bootcamp. So, in today's session, we'll be dealing with the implementation of variational autoencoders using the MNIST dataset. Okay, so uh, as prior to this particular session, you need a few libraries installed, which is you might have installed NumPy and Pandas for the previous session. The day two we covered advanced Python. We talked about Pandas and NumPy. We saw a couple of function methods as well. So in today's session, you will need two libraries mainly. One is PyTorch and the other is TensorBoard. Okay. If you are a Windows user, go on to CMD command line. Just type pip install TensorBoard, pip install PyTorch. Okay. So you may change the command according to your particular OS. Okay. Yeah. So initially there are a couple of um modules that you have to import. Let's see each one. So basically, various libraries are imported here. We are importing torch, torch.nn, torch.nn.functional, torch.utils.tensorboard, and torch vision for building the neural network and handling data. We need matplotlib.pyplot for plotting, datetime for timestamping TensorBoard logs, TQDM for progress bars, summary writer for torch.utils.tensorboard for logging. Okay, now uh, let's execute that. Okay, it's getting executed. It's taking a couple of time. That's expected because a lot of libraries are being imported together. It will take a couple of time. By the time we'll see what this is. Okay, this is basically torch.device. It's basically device setup. It sets up the device, which means like GPU if available, otherwise CPU. It's basically for modeling, model training and inference. Okay. Now we have some hyperparameters listed here. Hyperparameters such as batch size, learning rate, weight decay, num epochs, latent dimension, hidden dimension are defined for model training. Okay, we'll see where these hyperparameters are used. Yeah, it's still getting executed. Now, coming to this third code block, this is basically data loading and transformation. The input images are converted to tensors and normalized. The transformation pipeline includes converting images to float32 data type, scaling and flattening them into a vector. Okay, that's what basically we are doing. We are doing here. If you know some computer graphics, you would know what transforming, scaling and all is. Okay, so the transformation that we're doing here is scaling. I've set the scale value to true, which means the image is going to get scaled. Okay, now here we are downloading in here we are basically downloading and loading the training data. Data sets.mnist is used to download and load the mnist dataset. Data loader is created for both training and testing datasets to handle batching and shuffling. I've actually already executed all these lines of code. So because executing these lines of code requires a lot of time, so I'm not wasting that time during the live session. So I just meant to give you a warning that it will take time to load all this. Okay. Yeah. So this is how you are training the data set using the MNIST data. Okay. Here I'm downloading and loading the test data. Here what I did is the training data. Okay. Now this is basically the data loaders part. So this is where I'm defining my VAE model. So I have a class called VAE output. So this is basically a helper class to store and organize the outputs of the variational autoencoder, including the latent distribution, sampled latent variable, reconstruction, and loss components. Okay. Now I have another VAE class here. So what that class does is uh, the encoder, as you can see, I have an encoder parameter here. So what this encoder does is it's basically a sequence of fully connected layers of layers with swish activation functions. Swish activation functions, basically it's sigmoid linear units. So the final layer outputs mean and log variance for the latent variables. I have a decoder as well. Encoder, I have a decoder as well. So what it does is it basically mirrors the encoder with fully connected layers that reconstruct the input data. Okay. Now I also have an encode function. What does it function do? It basically maps input to a distribution in the latent space. Okay. I have another function called reparameterize. So what this particular function does is it uses the reparameterization trick to sample from the latent distribution. Okay, I have a decode function. It basically reconstructs the input from the latent variable. Okay, now what this forward function does is it basically implements the forward pass, including encoding, sampling, decoding, and also optionally it computes the loss as well. Okay, this forward function. Now, we are coming to a model initiation part. Let's see if that first line of code got executed. I have kept some other line of code to execute in the meanwhile. So this is getting executed here. That's why the first one isn't getting executed. So as you can see, it's taking a lot of time to get executed. Time complexity is very high because there are a set of data points to download here. Okay, that's the delay here. Okay. So I think it's actually great that I started running the blocks of code prior to the session, although I couldn't complete it. Basically, there are only a few lines of code left after this. Yeah, we'll see anyway. Okay. Yeah. So we are done with this here. Okay. Now, uh, this part is basically the model initiation. So as you can see, model equal to VAE of, remember VAE is a class that we have defined before, and there's I'm invoking the to method of the VAE class. So what that does is it creates an instance of the VAE class with the specified input, hidden and latent dimensions, and it basically moves to the appropriate device. As said, as I said in the beginning, CPU or GPU, okay, whatever. Now, coming down, we have created an optimizer object here. What it basically does is, optimizer is basically used in Adam W, which combines Adam optimization with weight decay. Okay, why is that done? It is to control overfitting. Okay, if you have got some basic knowledge in machine learning, you would know what overfitting is, right? Yeah. So coming down to the next one. So just I'm just explaining this part out, this output as well. As you can see, you can you can see a couple of activation functions given here: linear, sigmoid linear unit, linear silu linear, and other than the both, I've got the sigmoid function as well. Okay, so that's what basically optimizer is. Coming down to the train function, it's, yeah, as you can see, it's the training function. The model is set to training mode by invoking the train method from the model. Okay. Now, for each batch, data is passed through the variational autoencoder and the loss is computed. We are computing the loss after each data is passed through the variational autoencoder. Okay. The gradients are computed via back propagation and the model parameters are updated. Okay. Now, initially I said that we are importing the datetime module and a couple of other modules in order to keep the log, right? So that's what comes next. So here I have the test function. The test function what it basically does is I'm setting the evaluation mode of the model. So for that I'm using the model.eval method. Okay, the model is set to evaluation mode. Okay, now similar to training, uh, okay, this testing function is basically similar to the train function that we saw above, but then as you know, testing and training are two different processes, and that's the difference basically here. The model parameters are not updated here. That's the only difference that I can tell you. Then but instead of the model parameters being updated, what we're doing here is performance on the test set is evaluated. Okay, we are evaluating the performance based on the test set here. Okay, in the test function. Okay, I said about logging before. So every 100 steps the training loss and gradient norm are logged using TensorBoard. That's why we needed TensorBoard. Okay, this is basically the reconstructions and log random samples from the latent space. Now coming down, this is basically the model training loop. This for loop is basically for model training for a specified number of epochs, basically num epochs. The model is being trained and tested. After each epoch, the model's performance on the test data is evaluated. Okay, and the evaluation is not yet over, I see. Yeah, it's basically the 16th epoch out of 50, and it will take a lot of time. Yeah. So moving on to the next set of code. So what is being done here is it's basically visualization. We are going to visualize. We can see PLT, matplotlib dot pyplot. We are importing it as PLT. We are aliasing it. So after training, random samples from the latent space are decoded to generate images, which are then plotted and saved. Okay. Now we have got the latent space visualization as well. As you can see here, the latent variables basically Z for the entire training set are encoded and plotted as a 2D scatter plot. Okay. Now 2D and 1D histograms of the latent variable are also plotted to visualize their distribution. Now, coming to this latent spaces, we are basically, let's see what this interpolation is basically is. I'd also like to talk about the interpolation part here. Okay. Yeah. So what interpolation basically is, it's interpolation between 2 points in the latent space is performed in order to generate and visualize a sequence of images. Okay. That's why we are interpolating it. Now we need to save all these plots, and for that we are saving it as .webp files. As you can see here, we are saving it as .webp file. We are saving the figure as vaemns.webp. Okay. Now uh, you might ask the question why we are using this webp file format. It's basically in order to reduce the file size. Using webp file, it is more efficient because yeah, it reduces the file size. Okay. Now there are a few key concepts that I would like to talk about. Variational autoencoder is basically a type of generative model that uses variational inference to encode input data into a latent space and then encodes it back to reconstruct the original data. Okay. Now talking about latent space, the compressed representation of the input data is called latent space. Variational autoencoder basically learns a distribution over the space. Okay, we also talked about the reparameterization trick. Okay, so that basically allows back propagation through the stochastic sampling process by expressing the sampling as a deterministic function with a random input. Okay, you also saw what KLD is. KLD basically is the divergence. KL divergence It's a regularization term that ensures the learned latent distribution is close to a standard normal distribution. Okay. Now, this reconstruction loss as well. Reconstruction loss is it basically measures how well the variational autoencoder can construct the original input from the latent space. Okay. Now, talking about TensorBoard, it's a tool for visualizing the training process, including loss curves and model outputs. Okay. So this particular notebook, the code contained in this notebook, is basically for training a variational autoencoder on the MNIST dataset. It allows us to visualize how the model learns to generate and reconstruct images, as well as explore the latent space. We have talked about what the latent space is. Okay, so that's basically about this implementation of variational autoencoders using the MNIST dataset. So with that, we are concluding today's session. So the activity related to today's session will be given out during the day 4 of the bootcamp. This is day 3. So in the next session, which will most probably be on Saturday, we'll be diving on to a major project. This is the minor project. I'll be sharing the notebook with you. It will be in the description of this video. Okay, so do download it and run it on your system and see how it works. Okay, in order to uh, get in order to understand what each code block represents, you can refer to this video later as well. Okay, so with that being said, I am winding up for today. uh, thank you everyone. Thank you. Have a nice day.